Okay, so let's talk about diffraction. We got a little bit farther in, I think, one of the classes than the other, so just want to make sure we all had the same information. We're going to spend one more day in class on Tuesday wrapping up diffraction and refraction. I'd like to have more time for you guys to experiment with these two things rather than listen to me talk about it. So um, it's good that you are watching and kind of getting the main ideas beforehand so that we can move a little faster in class. So anyway, diffraction, we talk about waves. Remember, diffraction is a property of waves, not necessarily a property of light. So keep that in mind. We oftentimes use light because we can see the diffraction pattern a little more easily and we can measure it a little bit easier than with sound. Sound, remember we did the little experiment in class where we walked around and listened to the interference pattern produced by the diffraction or the spreading out of sound. But it's a little harder to be definitive with the constructive and destructive points. Light gives us an easier way to measure it. But anyway, diffraction simply refers to when waves travel, they spread out. Um, for example, if I dip my finger in water, um, maybe here, then I'm going to get these ripples kind of moving out away from the source. As those ripples move out away from the source, as they interact with obstacles in their path or openings, they're able to move around and through different kinds of obstacles. This whole phenomenon is called diffraction, and it depends on a lot of properties of the wave. It's probably the most important thing it depends on is the wavelength of the wave itself, and we'll see how wavelength dependence on diffraction causes a lot of cool phenomena to occur. So diffraction is the refers to the spreading out part. So when we get a little bit further here in a minute or two, interference of two diffracting waves are what produces the cool patterns. The sound, loud and soft sound that we heard walking across the through the room, the bright and dark spots produced by a laser pointer moving through diffraction grating. That's the interference. The diffraction part is how it moves through those openings and how it spreads out away from the source, causing it to interfere with other sources or waves from sources that are spreading out too. So diffraction then, and this is trivial, but the whole idea that every point on a wave really is acting like the source of a new wave is called Huygens. That's a funny name, but I think he's Dutch or something. Huygens principle, and it's all about the spreading out. So if I picked really this point, for example, on the wave, is really like another whole wave spreading out from that point. So we talk about how do we draw waves. We can draw waves as, like this if we want to. We sometimes draw waves as wave fronts, right? We can also say that these wave fronts, we can say travel as a series of like kind of rays perpendicular to the fronts. So waves can be represented in multiple ways. Whatever works, right? Whatever helps us understand what's going on is the way we typically draw it. But so Huygens principle or diffraction really is about any opening or hole or slit, as we're going to use for light, is the source of this. It's like a brand new source of light. It's why I think we use the example in class. If if someone makes a loud noise out in the hallway, we perceive that sound to be coming from the doorway because the sound waves are diffracting through the door and we hear the sound coming from the door. We can't necessarily tell, we might be able to tell a little bit exactly where the sound is coming from. We just know that it's coming from outside of the door because we hear the sound coming through the door. That's diffraction. This is again a cool image showing, if we look out here at the ocean waves, we can kind of see these linear wave fronts that are kind of coming in from some distant source. And as they reach this breaker, this is what they do around beaches and things, they put breakers. Sometimes they're concrete, sometimes they're natural, and to break up the energy from these waves. But you can see as the wave moves through that now we have kind of a whole new source formed. Somewhere out in the middle of the ocean, when the original wave was created, it looks circular like this too, but as it moves farther and farther away from the source, the wave fronts become more and more and more and more um, flat. It's just like the Earth appears flat to us because we're so far away. Um, we're so close. I don't even know how to say it. So close to the Earth, it seems flat. But really, it's curved. We just don't perceive the curvature, just like the wave fronts, since they're so far away. We don't perceive the curved nature of them. So diffraction is the moving out. Here you can see it again. I love this picture because you can clearly see the waves are kind of coming in, something like this. But as they travel between these two rocks, they diffract through that opening. We can also kind of see diffraction around here because you see how water coming around this side and water coming around this side is creating kind of a shadow behind there. But then you see the crisscrossing going on here. We can see that there is interference happening. So diffraction and interference, the two properties kind of go hand in hand. Where there is diffraction, there typically will always be interference to follow. The wavelength dependence. So here's kind of the general rule. The smaller the wavelength or the higher the frequency, the more directional the waves are, which means that longer wavelengths diffract more than shorter wavelengths. So again, longer wavelengths diffract more. They spread out more than shorter wavelengths. It's why we hear the bass drum of a parade in this diagram. You could be a block away and you're like, where's the parade? Where's the parade? It's really hard to tell because lower frequencies like bass is very omnidirectional. It travels and spreads out so easily that it's hard to really tell where it's coming from. Whereas the sound waves produced by a higher frequency, like the flutes, are very directional. In your home theater, you put the subwoofer wherever you want. You put it in the closet, under the coffee table, behind the TV. But your little speakers that produce the higher frequencies, you got to pretty much point them straight at where you're going to be sitting. If you turn them sideways, it doesn't sound right because the higher frequencies are more directional. We also said in class that, if we looked back at the whole spectrum of electromagnetic radiation, those longer wavelengths like radio waves, very long, can be radio waves can be, 100 or more meter wavelengths. Those diffract really, really well. They use those for TV signals, satellite signals, communication signals. So wherever you are, unless it's South River High School, you can typically pick up those radio waves through diffraction. You don't have to be aimed straight at the source to pick it up. Whereas something like infrared, which is a shorter wavelength, if you look at the scale, it's by a pretty large, by about a factor of 100 shorter. Um, you get more directional waves. In infrared remote control, you got to point straight at the receiver or it's going to get blocked. It isn't able to diffract around, whereas radio waves would. This also um, helps to explain, if you're in a concert hall or something and you're sitting behind a post. This always reminds me of the Ram's Head on stage downtown Annapolis. There's a couple of terrible seats in there where you're right behind a post. I can easily hear sound if I'm behind the post, but I can't see the performer on stage. And this is really about the same thing we just said. Light, visible light, has a very small nanometer order of magnitude wavelength, which doesn't allow light to bend around that post, but the sound waves can. Now, the higher pitch sounds may not sound great behind the post, but I can still hear the sound, whereas I can't see the light. And that has to do with the wavelength dependence on diffraction. This also explains why we see a nice, not today, this is Tuesday, it's kind of crappy out, but this explains why we see a nice blue sky. The light from the sun is actually white light. It produces wavelengths the entire visible spectrum. So if I combine all of these wavelengths together, I get white light. And we know that the sun actually produces um, radiation in the UV all the way to the UV. So it produces all of those. We're only able to see the visible ones, and when they combine, we get light. So why does the sun, when we look at it, not look white? It has more of a yellowish tint to it. And as we go on in the day, it actually becomes more and more and more of an orangish color. Well, it's all about diffraction. Remember, light has very small wavelengths, and if we look at the actual, remember, if we look at the spectrum here, we're getting longer, increasing wavelength of light as we move from blues to reds. So those longer wavelengths are able to diffract through. Now, our atmosphere is not a vacuum. There's stuff there. There's dirt and dust and um, particles and atoms and all kinds of things in the atmosphere. These wavelengths are these light particles or beams have to diffract around. And again, they're very, very short. It's not like blocking your infrared signal with your dog. It's blocking even smaller wavelengths with just atoms or particles of dust. So the particles that are easily diffracting through are the reds, the orange, the yellows, the greens, and then we get up to the higher wave or the higher frequencies, lower wavelengths. Those blue, violet doesn't come really through much at all. A lot of the violet gets scattered in the UV. We're protected by our atmosphere from the UV, and that's the whole issue with the ozone layer is that it doesn't. Once that ozone layer starts to go, it doesn't block the UV radiation from us very well. But those blue wavelengths get what's called scattered. So they're just kind of reflecting and bouncing around in the atmosphere. They're not able to move around particles. They just get kind of bounced from particle to particle. And it gets kind of stuck in that atmosphere, just kind of bouncing around. So when we look up, we see this blue sky because all the blue wavelengths of light are getting scattered around where all the other ones are making it through. And when you take out the blues, Roy G. Biv doesn't combine to form white light anymore. It starts to look more yellow when you start to kind of filter out the higher energy blue light. So as the day goes on and the distance from the sun to us gets greater, right, as the Earth turns and we're looking at more of a greater distance, um, towards the sunset or the sunrise, well, more of the light gets filtered out, and we start to get even more of the blues and the greens, and then the light starts to look more and more red and orange as we filter out more of those short wavelengths lights. So that's part one. We're going to get into the calculations in part two, so bear with me here.